Okay, good afternoon. I'm pleased to introduce two of our own graduate students. The first speaker is Ahmed Ibrahim. He'll be talking on optimization of pre-stress concrete transmission force under high intensity wind. Ahmed graduated from Cairo. He did his bachelor's and master's from Cairo University in Egypt, and he's a student of Dr. Azamati. And during his undergraduate, in fact, he stood 9 out of 450 students. The second speaker, Randy, he's sitting here, Randy Van Straten, will be talking on improving access to the frost dynamometry methodology for assessing brick masonry freeze town degradation. And he did both his bachelor's and master's degree from University of Waterloo. And he's Dr. Pop student. Dr. Pop is among us today. And he's NSERC IPS winner with Building Science Corporation. And without any further ado, I would like to invite the first speaker.
Thank you, Dr. Germa. Good afternoon, everybody. I will talk today about the optimum design of pre-stressed concrete transmission pool under high intensity wind. The outline of the presentation, I will start with the introduction, then overview and the objectives of the study and the methodology conducted, and an example for the optimum lecture design of pools and conclusion. As a start, the transmission line structure's main components are the supporting tower, the ground wires, the conductors, and the insulators. There are many types of pools that can be used: concrete pools, steel pools, and wooden pools. The benefit of the concrete pools rather than other pools is the low installation cost, low maintenance cost, appropriate delivery time, and the resistance to insect attacks. There are many cross-sections of the concrete pools that can be used, like hollow circular sections and hollow hexagonal ones. Hollow square sections also can be used. And the dimensions of the concrete pools can vary from the top to the bottom with a tapering slope. According to the structural systems used, there are many structural systems that can be used, like cantilever structures, or guide pools, or frame pools. I'll talk about the pre-stressed concrete pools, the loads affecting on it, the failure reasons, and the structural modeling of such pools. And we will talk a brief about the high intensity or the local high intensity wind events such as downbursts and tornadoes. The loads acting on the pre-stressed concrete pools are its own weight, the normal wind, high intensity wind, maintenance loads, and ice loads. The failure reasons of such pools is attributed to the extreme wind loads on conductors, the differential shrinkage between the outer and the inner layers, segregation of concrete and poor concrete mixing, rusting of reinforcement, vehicle impacts, and improper embedment. The structural modeling of such pools should take into consideration the material nonlinearity, the geometrical nonlinearity, and time-dependent material properties, which are the losses that might happen to the pre-stressing strengths in such pools, like the shrinkage, creep, and strength relaxation. When the velocity of the wind exceeds 45 meters per second, it can be considered as high intensity wind. And this high intensity wind is the reason for 90% of the structural damages due to wind. When the thunderstorm is formed, it consists of updrafts and downdrafts. The updrafts are formed from the warm air going up, causing tornadoes, and the cooled air going down in the form of a jet with a specific velocity and specific diameter hitting the ground, and the velocity spreads everywhere, causing forces on conductors and towers, and this is named downburst. For simulating the downburst wind field, computational fluid dynamic simulations are conducted by Hanger and Kim in 2004. Each particle in space has radial and vertical velocity components, And a parametric study was conducted by Shihata et al. In 2005. It was found that the radial velocity is the measure compared to the vertical velocity, and the maximum peak happened in an instant, so a static analysis is performed. And there are many parameters that are affecting the downburst events, like the jet velocity and the diameter of the jet itself, the distance r, which is the distance between the center of the tower and the center of the downburst event, and the angle theta, which is the angle between the perpendicular to the transmission line and the line joining between the center of the tower and the center of the jet. For simulating the tornado wind field, computational fluid dynamic simulation are conducted by Hanger and Kim in 2008, and it was found that each particle has radial component of velocity, vertical component, and tangential component. Okay, so the objectives of the current study is to develop a numerical model to analyze the pre-stressed concrete pools under downburst and tornado loadings, and using an optimization technique to achieve the optimum design of such pools under high-intensity wind events. For the validation of the numerical model, two cross-sections, two pre-stressed hollow circular cross-sections are used. Various outer diameters, various inner diameters are tried, various initial straining of the strands, and different number of strands are used, 4 and 8, and different area of strands is tried, and different compression forces acting on the cross sections. And the moment curvature diagram is compared with the Response 2000 program, and it shows a great agreement for the two cross sections, so that the moment curvature diagram for a specific compression force can be obtained for such cross sections. By integrating the curvature along the pool height, we can get the top deflection, and for validating this technique, it was validated with a pool that is tested by Fayed et al. At 1994. This pool was 27 meters high, and this was the load deflection with the blue chart, shows the load top deflection, and with the red chart is the developed technique, load top deflection, and it shows a great agreement, and a slight increase in the maximum load that can be sustained by the pools rather than the test that was attributed to using nominal material factors equal to 1, and some deterioration that might happen to the material properties a long time that might decrease the maximum load that can be sustained by such pool. So we have now computational fluid dynamics data. We can compute wind velocities on the tower and conductors, and then assume pool dimensions and tapering slope, then calculate the induced forces and straining actions on such pools and conductors, design for axial and bending stresses, checking if the section is adequate or not. If it's not adequate, we will assume new pool dimensions and tapering slope, scale the computed loads according to the new cross-sectional slope, then design for axial and bending stresses. If the section is adequate, we can determine the number of strands, checking if the section is adequate or not for shear and torsion. If it's not adequate, we will choose a new section and repeat this process again of scaling the computed loads. If the section is adequate for shear and torsion, we will determine the head reinforcement, draw moment curvature diagram, and integrate this curvature along the pool height and determine the drift or the top deflection due to various local intensity wind events. Okay, so for optimization, we apply all the possible downburst and tornado cases under, we apply the local intensity wind events, all the possible tornadoes and downburst cases on the concrete pools, and we assume different pool dimensions and tapering slopes, and there are some constraints in the optimization techniques, like the adequacy of the section for resisting axial and bending stresses, the number of strands, so that the minimum spacing shouldn't be as the code recommendations. And the adequacy for shear and torsion is also a constraint for the optimization technique. And the top drift should be within the allowable in the provision. This is an example conducted for a 35 meters cantilever pre-stressed concrete pool. There are various numbers cases applied on this pool. The diameter of the jet itself varies between 500 and 1,500 meters. The distance R over D varies between 0.8 and 2. And the angle theta, which is the angle of inclination of this event, varies between 0 and 90. So a total number of 539 load cases has been studied. And the envelope of the bending moment due to all these cases is determined. And the optimized section, at the first column here, it's a 35 meters cantilever pool. Every node has its specific height, and the outside diameter and the inside diameter at the top are 0.514 and 0.3. And at the bottom, it reaches around 2 meters and 1.8 meters hollow. So the thickness is around 10 centimeters in resisting all these downburst cases. And this shows the capacity of the concrete pools after the optimization technique. The conclusion of the study is that we have reached a numerical model to analyze cantilever pre-stressed concrete transmission pools under various loadings, and it was verified with load test that was conducted by Fuad et al. At 1994. And the behavior of the pool can be detected under various high-intensity wind loadings, and the optimal design of cantilever pre-stressed concrete transmission pools was achieved under various high-intensity wind events. At the end, I would like to thank Dr. Ashraf El-Damati for his support and thank Western University for giving me this opportunity. Thank you. Any questions?
Yes.
How do you convert the wind speeds from the CFD simulation to the aerodynamic force?
I use the equation recommended by the code, multiplying half by rho by d squared by the drag coefficient.
Which drag coefficient did you use?
I used it 1.